So I wanted to do one more example of an ideal gas law problem from the notes. All right. So there's a couple things about the gas law problems that the ideal gas law problems that are a little bit different from the ones that we learned earlier. And one of the things about doing these problems is that you really need to pay attention to the units of the measurements that you're putting into the problems. All right. So the reason that the units matter is that you need to make sure that the units that you're putting into the equation, into your equation, match the units that are in the R value. All right, and again, the R value can be one of three values. All right, they're actually the same value. It's just it depends on the units of pressure that you're using. If you're using an atmosphere as your unit of pressure, you would use this one. Millimeters of mercury would be this one right here, or kilopascals would be this. All right. Another thing though, notice that the volume, this is a liter right here. So if the volume in the problem is not in liters, you need to convert it to liters. All right, because all of these numbers assume that you're using a volume which is given in liters. All right. So when we look at this problem, first of all, how do we know it's an ideal gas law problem? All right. If you take a look at it, there's nothing that would indicate that a change is occurring. All right. You're just talking about a sample of gas that has a particular volume, temperature, and pressure, and just saying, well, how many particles are there, or how many moles are there? All right. So we can start to. There's a couple things that we can identify first. All right. First of all, in this problem, all right, what value of R are we going to use? All right, because we know that we're going to use PV equals nRT, and the value of R depends on the units of pressure. All right, so here's our pressure. All right, 750 millimeters of mercury. All right, and because we're using millimeters of mercury, if you look at the values for R in the reference guide, you'll see that the one that contains millimeters of mercury is the 62.4 you say liters, millimeters of mercury per mole per Kelvin. All right, I don't care that you can say it, but that's how you would say this if you wanted to. All right, so make sure that you choose this particular value for R. All right, another thing about this is that notice since it gives liters as your unit, but the volume given in the problem is in milliliters, we're going to have to convert that to liters. All right, so to convert 890 milliliters to liters, we're going to divide that by 1,000. All right, and if you look at the problem, how many moles? Moles is N, so that's what we don't know in this problem. And everything else we can pull out. All right, notice that your temperature is in degrees Celsius in all gas problems. This needs to be in Kelvin. All right, so that's going to be the value that we use for temperature. And as we said, this is your value for your pressure, and that means we're going to use this particular value for R. All right, so in terms of the math, all right, start off with, it is possible that you can take this and then plug your numbers in there right off the bat. I prefer to solve for the variable. All right, so we don't know N. All right, so if we get N by itself, that would end up giving us this expression right here. Again, this is done by dividing both sides by RT so that you get rid of these two variables right here. So we have this equation right here. And what we're going to do at that point is we're just going to plug in the different values. All right, so our pressure is this right here. Our volume is 0.890 liters. Here's our value for R, and here's our value for T. All right, and so one thing that I think helps out is if you just put parentheses around, you picture each of these variables as having parentheses around them. All right, and when you get to a particular unit, put parentheses around the whole thing. All right, notice that this is the entire value for R. All right, but I've put every single thing in the denominator. All right, so notice here's your fraction line right here, and everything is in the bottom. All right, this is important because you're eventually going to have to plug these numbers into your calculator, and you need to make sure you know what things are in the numerator and what things are in the denominator. All right, so the numbers part, pretty much treat it as these two numbers are in the numerator, these two numbers are in the denominator. You'll get an answer, and make sure that you round this particular problem to 2 significant figures, because this has got 2 sig figs here, this has got that's got 3 sig figs there. But so this right here would dictate the number of significant figures that you have. All right, so that's rounded to 2 sig figs. But why is the answer in moles? All right, well, there's 2 reasons for that. The one that might be the most obvious is that the question is asking you for moles. All right, but the real reason that the answer is in moles is when you look at your units. All right, after you plug this in, all right, notice that your millimeters of mercury would cancel out. Your liters would cancel out because you see them twice. All right, and your degrees Kelvin or Kelvin would cancel out. By the way, when you're talking about this, when you see this number right here, well, when you see this number right here, you would say 21.0 degrees Celsius. But when you're talking about Kelvin, all you do is say Kelvin. All right, you don't say degrees Kelvin. It's just, this is 294 Kelvin. All right, so anyways, this is a little bit of an oversimplification, but for these problems, it works. Whenever you see a unit twice, they would cancel out. So the only unit that would be left over here is moles. All right, and so that's why your answer is going to be in moles. All right, so hopefully that helps out. Make sure that you practice these problems so that they become very second nature. All right, thanks, guys.